Hi, welcome to this module. In this module we will be looking at two different technology for depositing metal, insulator and semiconductor materials. Now in the last module what we have seen? We have seen a thermal evaporation system, and I have also shown you two different YouTube videos, right, that will help you out to understand how the technology works. Like I promised, we will also show you the E-beam evaporation and thermal evaporation in the clean room. Now, what was the disadvantage or limitation of thermal evaporation, right? If you think about it, thermal evaporation is where you have a source on which you load the material and then you heat that material. When the material reaches its melting point, it will evaporate and it will deposit on the substrate, is not it? So, the difficulty here is that if the source material that you are loading on the source, if the source material melting point is higher than the melting point of the source holder, then instead of melting source you will be melting the source holder, and that is not acceptable because we want to evaporate the source and not the source holder, isn't it. So, that is the difficulty, that when the material that we want to deposit, its melting point is higher than the source holder, then we cannot use thermal evaporation. In that case, what can be the alternative technique? So, if you see the slide, what I am saying is, if you have a source, this is a source holder, source holder can be also a coil like this, right, and if I load the material in the source holder, which is called my source, in this coil we will load this kind of wires, alright. Let us say this wire is aluminum, right, and this material is also aluminum. Now, the source holder material, this is called boat, by the way, boat, BOAT, and this is our coil, right. So, the source holder material, whether it is a coil or it is a boat, right. So, I will write down the source holder material melting point should be greater than the source material melting point. This is source holder, the holder that can hold the source, for example aluminum. The coil is also a source holder, it can have aluminum wires loaded onto the coil, isn't it. Thus, the source holder material melting point should be extremely high compared to source material, that is your aluminum. So, if this is the case, your when you heat this board by applying a voltage or right higher voltage, because this is a resistance. So, the current will flow, and because of the current, the Joule heating I square R, the material that you are loaded will get evaporated, isn't it. However, if the source holder material melting point is close to or equal to source material melting point, then what will happen? Then the coil will start evaporating or the boat will start evaporating rather than the material loaded onto the source holder. That is the difficulty, alright. So, what can be done alternative to this kind of problem? The alternative is, instead of heating the source material or the source holder material, what we will be doing? So, instead of heating boat or coil, what we will be using is a crucible. Crucible again is a holder, right. So, we will use a crucible and then we will load the crucible with the material, and instead of heating the crucible with some by applying a voltage or by applying a power, what we will be using? We will be using electron beam. Electron beam will be incident or will be we will use electron beam as a source point to heat the source material and evaporate it. In this case, your substrate or your source holder need not be conductive. The source holder material need not be, it should not be conductive, it is fine, it is not conductive. In thermal evaporation, we require the source holder to be conductive, right. So, if I use E beam, then E beam will only heat the substrate source material and it will melt it and evaporate it, alright. So, now you are using electron beam to melt the material instead of hitting the entire source holder, that is called electron beam evaporation. So, let us see in the next slide. This is what I was talking about, that you have a crucible which you can see here, and then you have a source which is right over here, and then this is a molten source. Molten source is because electron beam which is generated from the filament, it is accelerated through the accelerating electrode and it is bent through the deflecting magnet, and then it is incident on the source. So, when it is incident on the source, it will melt the source and the source will start evaporating. So, that is the phenomenon of electron beam evaporation, the mechanism of electron beam evaporation. It is extremely powerful technique and it can evaporate materials that are difficult or even impossible using standard thermal evaporation technique. Some of the materials are like titanium, or we can also deposit silicon dioxide and alumina. And then in this case is an actual photograph or the E beam system. This is the source, this is the source, okay, and the source is loaded in a crucible and the electron beam will come from here and it will incident on this source like this, okay. And because you are heating it, the source material will be evaporating. This is the shutter. Shutter is to stop the evaporation, because when you evaporate it, if you reach, let us say you want to deposit 1 micron film, as soon as you reach 1 micron you should start you should stop the evaporation, but when you stop the electron beam, this metal will be at extremely high temperature and still it will evaporate for some time. So, if you use this shutter, then the substrate will be the material will not get deposited on the substrate which is above the shutter. What I mean is, above this particular shutter there is a substrate, alright. Of course, the substrate size is smaller like this, okay. Now, when the shutter is open, then the it was depositing material, right, and when the substrate is closed, the material will get deposited on the on this shutter. This is a substrate. When the substrate is protected by the shutter, then the material is deposited on the shutter and not on the substrate. Thus, you can only control 1 micron or even below. So, this is nothing but a shutter. This is for in a very easy terms, you to understand that you can use shutter to stop the evaporation. Now, you see this material here. This is a there can be many way of holding this electron beam evaporation sources. One is a single pocket, then there can be rotary pocket and there can be linear pocket. So, what is pocket means? This here, this one is a pocket, right. This is a pocket. If the pocket can only hold one source, single pocket. If it is rotary, that means that there is 1, 2, 3, 4. So, this one here is a rotary system. This is one is here, second source will be here, third will be here, fourth will be here. So, you can deposit multiple source using the rotary system. Then there is a linear pocket where the source is the pocket for holding the source is in linear fashion like this, right. So, that is what the evaporation sources holder means. So, this is the for the single pocket, this is for rotary pocket and this is for linear pocket. alright. So, if you go in detail, then a water cooled copper block is bored out to have a pocket in the shape of inverted truncated cone, which is right over here, right. This is water cooled so as to keep the other area of the material at lower temperature except the electron beam area, which is here where the source is loaded. Source material placed within this pocket. So, where is the source material placed? Within this pocket. So, when I say within this pocket, where it is? It is here, here. Okay. So, if you see here, this one is a source, right. So, this is loaded within the pocket. Now, the crucible has a smaller or similar pocket within it. A magnetic structure consisting of permanent magnet and 2 pole extension are located around the block such that its field lines run parallel to side of the pocket, such that when the electron beam comes, it will only incident in this area and not some other area. On the same slide of the block is a filament which produces electrons by thermonic emission and is formed into a beam. This is called emitter assembly. So, this goes all the way down. You cannot see anything which is emitter assembly when you open the system, like here you cannot see anything which is below this guy, correct. So, this is the what is written here. The electron beam is steered by these fields in a 270-degree arc to impinge on the center of pocket. Electron energy is controlled such that magnetic field bend it precisely into the center of pocket, alright. Then the addition is that an electromagnetic coil known as sweep coil is employed to effectively raster the beam around the surface. So, what happens is, if you have the source, if I just incident the electron beam only in one area, this area will get melt, but what about other area, what about this one, right. So, instead of that, if we have the raster scanning of electron beam on this particular source, then it will scan like this, right, or if depending on horizontal scanning or vertical scanning or raster scanning. So, the raster scanning is possible if we use the electromagnetic coil and it can sweep in XY direction. Variety of sweep patterns are used in control program for electromagnetic coil. Materials with high performance high melting point require XY sweep to prevent the E beam from boring a hole. High melting point means you have to this is a material, right, loaded onto the source holder. If I just keep on incidenting electron beam on single spot, because the melting point of this material is extremely high, it will start like making a after it evaporates, it will start making a hole into the holes into the it will form a bore, right, form a boring a hole into the melt. This is a melted area, right, and subsequent spitting which creates large nodules of source materials in growing thin film. So, what happens is, when you let me reiterate, when you have a source and if you have a single spot of E beam rather than raster scanning, what will happen is this will start melting the source, and when it starts melting, because melting point is so high, what will happen, the chunk of this material will also get melt, and in the substrate, instead of having a cool uniform thin film, what we will get is a substrate with some chunk in between. Film will be there, but it will not be uniform and some chunks are available. Why? Because here the heating is non-uniform, alright. So, this will happen when you do not use the XY sweeping. When you do not use XY sweeping, then the difficulty is with the large nodules of source material depositing when you are growing the thin film, alright. Now, if we talk about the rotary pocket, instead of single pocket, if I use rotary pocket, then the electron beam source has all the same parts as a single pocket unit, except that the water cooled copper block is essential a turret of multiple pockets, each of which can be extended into position. With this design, a number of different materials can be evaporated, because you have 4 source. So, you can have aluminum, you can have chrome, you can have gold, you can have titanium. There can be multiple sources possible to evaporate. At a single time, only one source is available for you to evaporate, alright. But you can load multiple sources, that is the advantage of rotary pocket. With this design, number of materials can be evaporated sequentially, not simultaneously, sequentially from a common magnet emitter sweep coil structure. Obviously, this design includes shielding to prevent the cross contamination of the source. So, this is a shield this is a shield, right, and exactly this rotary pocket is in here, right. You see this is the system with rotary pocket, is not it. So, rotary pocket, this is a shield, so that it can prevent the, when this gets evaporated it will not deposit on the other sources, it will not deposit on other sources. So, it can also act as a shield to prevent the cross contamination. Okay. The final pocket or evaporation source is linear pocket. A linear pocket e-beam source is similar to rotary pocket, except that its pockets are arranged in a line, are indexed into position in a linear fashion with a common magnet into coil structure. So, this is like whatever you want to evaporate, this guy will go in this direction and here is the e-beam. So, once it is there you can just move it. So, this bar can move all the way here, right. So, it is just only this area is exposed. If you want it you can pull it on this way or you can pull it in this way, right. So, this bar can go here or can go here, depending on the source that is exposed to e-beam we will get the material deposited onto the substrate. Substrate is what? Substrate is silicon wafer or any material on which you want to design or fabricate the sensor. So, let us see the two videos about introduction to e-beam and then detailed about that. So, let me play the video.
An electron beam evaporator, a type of physical vapor deposition tool, is used to coat one side of a sample with various metals. Commonly used metals on this machine include aluminum, platinum, gold, chrome, nickel, copper. Once a sample has been loaded, the chamber will be closed. The chamber is then pumped down to a very low pressure. The machine then releases electricity through a filament. Several magnets are used to direct the electron beam from the filament to a crucible containing the target metal. The metal then heats up and begins to evaporate onto the shutter. This process can take several minutes. This is similar to a pot of boiling water on a hot stove. A sensor within the chamber is used to determine the current rate of evaporation. Once the desired rate is reached, the shutter is open and the sample is exposed to the evaporating metal. The desired rate of evaporation and the amount of metal to be evaporated can be set under the deposition controller. Once the desired amount of metal has been evaporated, the shutter is closed. The pressure inside the chamber is then increased to atmospheric pressure and the chamber is opened.
Okay. You have seen the first video, right? Let us see the second video as well.
This is the e-beam. It is used to deposit metal or even silicon dioxide onto your substrate. What it does is it uses an electric gun to heat your sample material, and that will evaporate onto your substrate in the sample up here. So before you can use the machine, you need to be trained and qualified. And once you get those two things accomplished, you'll get an account to log in. So when you come to the system, you want to make sure nobody else is using it, the system's not down, and then those are all fine, then you come in and log in. Once you've logged into the system, you want to write into the logbook. So in the logbook, you would write your name, your time you're using it, the material you're depositing, the base pressure, and then once you log in, you are ready to start loading your sample on a substrate. This is the phase of loading your samples into the e-beam. There are two types of substrate holders. This one is for whole wafers, while there's another one over here where we can put smaller pieces of wafers as well. And you can actually mount the whole wafers there as well. So if you look at this sample holder, we put the wafer on here, and then we're going to clip it onto here. Because actually this whole thing is inverted in the machine, so you don't want it to fall, the sample to fall. I use clips, but you can also use the thermal Kapton tape. So once you've mounted your wafer and you want to put it in the system, you would need to vent the system, because right now it's in high vacuum. So what we're going to do is now we're going to vent the system. So now that we've been venting the system and the pressure has reached 7.4 to 10 to the plus 2 at ATM, we can actually open the chamber. So to do that, we would turn the vent off and raise the chamber with the toggle valves. You push it back because there's two pins right here. Right here is a pin. So you know how back to push it. So once we have our sample and substrate loaded up here, we want to actually load in our crucible that contains the metal that we want to evaporate. So this system actually has 4 pockets that you can put this in. So to put it in the right pocket, we would need to first use gold as a reference. And since we're doing titanium, we want to be 1 before gold. So we have gold, we look for gold, and then we rotate the system with this knob here. And we can see the open crucible for titanium, and that's where we put it in. So we'll do that now. We'll open the shutter so we can see our samples. So we can turn this till we find gold. So if we look inside, so we can keep turning it. And gold is right there. So we know that it's one after the gold. So we know this is the slot for titanium. So we put it in here. We make sure it's in. And then we close our shutter. It's also good to look at these 2 mirrors. So these mirrors help you look at your crucible when you're depositing. This mirror lets you see your crucible when the shutter is closed. And then this mirror lets you see the crucible when the shutter is open. So you put your head about this height and to make sure you can see the mirror there when the shutter is open. And then the mirror there of your sample of the crucible when the shutter is closed. So I can see the crucible there when it's closed, and I can see the crucible there when it's open. So my mirrors are in the right position. So now that the sample is closed, and the substrate is there, and the shutter is closed, our mirror is in the right position, and we have a sample up here mounted securely. We can bring this chamber down and put it back into high vacuum. So we're going to do that now, is we're going to lower the chamber. So now that we've closed the chamber, and our samples are in there, and our crucible is there, and the shutter is closed, we can begin the pump down process. So right now the system is in atmosphere, normal atmosphere. So we want to bring it down to the high vacuum. But we can't just jump there, so we need to rough it with a mechanical pump. So the first thing we're going to do is turn the mechanical pump on, which is called a roughing. So there's a roughing valve here. And we just turn it on. Make sure the high vac and the vent is off. So we turn the roughing on, and you should see the pressure decrease. So we want to make this to make sure that the pressure is less than 7 times 10 to the minus 2 before we turn the high vac on. But you can go a little even lower than that. So we'll wait a little bit for the pressure to drop. So after the roughing pump has brought the pressure down to below 50 millitorr, we can switch the mechanical pump off for the roughing and turn on the high vac. So what we do is we look at the pressure, it's under 50 millitorr. And now we're going to turn the rough off. And once we turn it off, we wait a little bit for the actuation of the pneumatic valve to make sure it's closed. And then we're going to turn the high vac on. So when we turn the high vac on, after we turn this on, we should see the pressure drop. So let's turn the high vac on. And you can see the pressure drop fast. If the pressure does not drop, there might be a problem with the cryo pump. It might have been dumped. To verify that, we would look at the cryo pump, which is located behind the system. And we want to make sure there's no moisture on top of the pump. If there is moisture, that means the cryo pump has been dumped, and we want to abort the process. So to abort the process, we would turn the high high vac off and then go to the chase and turn the compressor off. In case the cryo pump has been dumped, you want to make sure you turn the compressor off. The compressor is found in this chases room 2337. And before you go on, you want to make sure there's no odors or chemical spills. If there is, then you will notify staff. But it looks like it's fine to go in. So we're going to go in and turn off the compressor. So this is the compressor for the E-beam 1 cryo pump. So it's labeled E-beam 1. So it's bottom one. And if the cryo pump is dumped, you need to turn the switch off. So the switch is located here. And you would turn this off if the cryo pump is dumped. After it's turned off, then you notify staff and let them know that the system has been dumped. So we're going to wait till the high vac goes in the -4 range. And when it goes in the -4 range, we're going to turn the ion gauge on. So we'll just wait for the high vac to pump down. Once the pressure of the thermocouple has reached its maximum scale, so we can't go any lower, we turn the ion gauge on, which is actually measuring the true pressure, because this is meant for low pressure measurements. So we turn it on, you can see the pressure is 6.8 to 10 to the -5. So we watch the system, and we can make sure that it's in high vacuum. And if it is, we can leave the clean room and come back after about 2 hours and then get ready to deposit.
So what you understood? You understood that how the E-beam evaporator would work, what are the sources within E-beam evaporator, what is the advantage of E-beam evaporator over thermal evaporation, right, and what are the different kind of pockets available if you want to have multiple sources, is not it. Now this E-beam evaporator or thermal evaporator both are based on the heating, and that is why it is a bigger umbrella is thermally the thermally evaporating or electrically heating the material, because in both the cases either it is electron beam or heating the source holder, we are using a electric energy, right. So either we are heating it up with the help of a power source or we are using electron beam, and in both the cases we are melting the material and then evaporating it. There is one more technology that is used for depositing this film, and that is called sputtering. Sputtering is a mechanical way of dislodging the atoms from the source and depositing onto the substrate. Now if you have seen when there is a metal roof and if the rain falls drop by drop, the sound that comes, if it is tuck 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 tuck, right, this is sputter. So that is why from that phenomenon it is called sputtering, because here also it feels like a raindrop, but instead of raindrop we are using atoms to dislodge the, so the gas is used to dislodge the atoms, and atoms fall onto the substrate and deposit a film. So it is like 1, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th and so on. So let us see the sputter deposition. You can see here sputter deposition system. The source is on the top and the substrate is on the bottom, alright. And what happen is that when you have a vacuum and you introduce argon, then argon ions will dislodge the atoms from the target, and these atoms, which is target atoms or you can say source atoms, will get dislodged mechanically, because argon ion will hit it, and when the target atoms are dislodged it will move towards the substrate. Our substrate is a wafer, right. So every time when you have a high vacuum, this phenomenon occurs. Under introduction of argon, there will be plasma generated, and this argon ions will dislodge the target atom, and this target atom would travel towards the substrate or a wafer, creating a film. The advantage of this particular system is that we can deposit alloys and compounds better than evaporation technique, better than E-beam evaporation as well as the thermal evaporation. So this is an actual system of a sputter unit. This is the chamber where the things happens. These are all the controls which are electronic control, and this is a vacuum system that will create a vacuum. So, this is how the sputter system looks like, and the plasma is generated by applying RF energy or RF signal. Target is bombarded with argon ions. We already discussed this. This ion knocks the atoms up from the target. Sputter atoms are transported to the substrate. Wide variety of materials can be deposited because material put into the vapor phase by the mechanical rather than a chemical or thermal process. So, this is like mechanical dislodging or mechanical way of depositing the film. The other advantage is that there is an excellent step coverage of the sharp topologies, causing large number of scattering events. Finally, film stress can be controlled to some degree by chamber pressure and RF power. Now, what are the sources or for sputtering? The sputtering process can be done in two modes. One is called DC sputtering, another one is called RL sputtering. Sputtering can also be magnetron. So, if it is a magnetron sputtering, then you can say DC magnetron sputtering and RF magnetron sputtering. Major process parameters are given over here, right. The sputtering is one of the most used equipment in thin film deposition. In addition to IC industry, several other industrial products use sputtering, whether it is computer devices or hard drives, hard coating for tools, metals on plastics, LCD, and the reason of using it widely than evaporator is because there are very few things one can do to tailor the film property. The step coverage for the evaporator is poor. It is not suitable for compounder alloy when you talk about evaporation unit, and finally considerable materials are deposited on chamber walls and wasted, while in case of sputtering it is not so. These are few targets that are used for inside the sputter system. So, let us see again two different videos to understand the sputtering system, and then we will compare the advantage and limitations of the sputtering system. Let me play the first video.
The use of thin layers of materials is a crucial need in many industries. Architectural glass, displays, and touch panels or solar cells all contain thin films. The most important coating process to produce these layers is called sputter deposition. How does it work? Sputtering deposition is done in a vacuum chamber. The most common substrate for the thin layers is glass. The sputter system can have different sizes depending on the application. The source of the thin film material is a planar or rotary sputtering target of metal, ceramic, or even plastic. Molybdenum targets, for example, are used to produce conductive thin films in displays or thin film solar cells. At this point, the process starts. Air is continuously removed by vacuum pumps. The base pressure in the vacuum is around 10 to the minus 6 millibar, which equals about a billionth of the atmospheric pressure. Argon gas is introduced continuously to achieve a low pressure argon atmosphere. A magnet array inside the cylindrical target generates a magnetic field. The target is filled with cooling water, which will dissipate the heat generated during the sputtering process. The targets are rotating so that the material will be utilized uniformly. A high voltage is applied to the molybdenum target and creates a plasma, which is concentrated along the magnetic field. The plasma consists of argon atoms, positively charged argon ions, and free electrons. The positively charged argon ions are continuously generated by electrons hitting the argon atoms. The sputtering target is negatively charged. Therefore, the argon ions are attracted towards its surface. Let's see what happens. The argon ions collide with the target and eject molybdenum atoms from its surface. This is what the sputtering process is all about. In a way, it resembles a game of billiards, don't you think? Layer by layer, the ejected molybdenum atoms are deposited onto the glass substrate opposite the sputtering target. But let's go back to the target material. No metal can be made 100% pure. Iron or chromium impurities in molybdenum targets are critical. Why is that? Argon ions don't distinguish between molybdenum and impurities. Impurities will also be sputtered and incorporated into the thin film. Nobody wants that. Impurities can negatively influence the thin film properties, the electrical conductivity, for example. Only highly pure sputtering targets can ensure high-quality thin films. And that's what Plan A stands for. We are the only manufacturer to supply molybdenum at a guaranteed purity of 99.97%. Typically, the material is even purer. It is this purity that our customers rely on to create the best products in the market.
Let me also play the second video also. Here you will see how this sputtering occurs, and in detail here you will be able to see in the second video you are able to see that what are the subsystems within sputtering. Right, that is why I particularly have selected this video, so that you can see the internal parts of the sputtering unit. Okay. So, that is the advantage of this one.
Hey everyone, I was finally successful in depositing a clear conductive layer onto a microscope slide. So this will be the basis for a lot of my future experiments in OLEDs and other display technologies. So let me show you how I did it. The device that's actually doing the depositing is called a sputter gun, and I machined mine from basic pieces of metal, and I'm going to unscrew it here like this, and eventually the whole thing just comes off like so. And down in the hole here is a spark plug, and it's facing up towards us. So on the underside there's the rest of the spark plug, of course, and then right next to it there's a needle valve with a hose coming off, and the hose runs to my argon cylinder. So I can control how much argon is getting into the chamber through the needle valve, and I can get high voltage into the chamber through the spark plug. And the underside of the sputter gun has a rod in here that contacts the top of the spark plug, so I have sort of a shielded entry into the chamber. The sputter gun itself is relatively simple in construction, so let me just take it apart and show what's inside and then describe how the whole process works. So the very outside is called a ground shield, and it slides off like this. And the purpose of this is just to keep the things that you don't want to sputter inside this. So when the shield is on, the only thing that's exposed to the chamber is the surface of this disc here, which is the thing that we want to sputter, to send off onto the microscope slide. So if we take that off, the rest of it is built like this, and between these two layers is an insulator. So we'll take this apart, and currently there's some changes that I'm going to make to this. These are nylon screws and nuts holding it all together, and nylon is not really a great vacuum chamber material. So eventually I'm going to upgrade this, but I'm not quite sure what I'm going to use instead. And so this part is at the vacuum chamber case potential. Let's just call that ground. And then the inner part here, this is where it touches the spark plug. This is all at a negative high voltage, let's say 1000 volts negative. So inside here, we've got a very high potential between this outer shell and the inner shell, but there's a few other tricks here that allow us to sputter just the target material and not sputter the rest of it. So I'll open this up, and as you can see, I'm missing quite a few screws because I haven't got the right ones in yet, and I just wanted to test this quickly. Inside here is a magnet, a ring magnet, neodymium ring magnet, and a steel pole piece that I turned on the lathe. And so the idea here is that when the magnet is inserted into here like this, there's a nice magnetic field on the top here, and you can even see one that I cracked my disc, unfortunately, so I'm not going to undo the top layer just yet, but also that there's a ring pattern where the disc has been eroded by the sputtering. I've also got some holes in here for a cooling system, which unfortunately I didn't have running yet, so that's hence the cracked disc. And the idea with that would be, this is a sort of a Teflon hose. It's actually called a plastic called PFA with an O-ring on like this. The hose can be sealed up to this, and then with an O-ring in the right spot here, this whole thing closes up and I can actually pump water through the copper block. So a lot of sputtering systems say they require water cooling, and I always thought that only applied to like systems that ran for 8 hours a day. I figured that the thermal mass of this block would be enough to keep me safe for a 5-minute run. But as it turns out, not quite. I'm not sure if this was due to my clamping or too much power or something, but I think water cooling is kind of a necessary thing if you want to sputter stuff at any reasonable rate. Okay, so let me tell you how this thing actually works. So if you want to make a nice uniform coating on something, say like a microscope slide, you have a few different options, and two of the most common ones are evaporation and sputtering. So in a previous video I described the evaporation process, and this entails heating up the material that you want to coat. Heating up the material with which you want to make the coating, and typically that's done in a metal boat like this. So what we do is pass a really high current through here. This thing becomes very, very hot, white hot even, yellow hot, and the material here evaporates and then condenses on the thing that you want to coat. So this is, roughly analogous to boiling water in the kitchen and then noticing water droplets condense on a cold window. The downside with this is that you have to heat up the material to that yellow hot temperature. So if your material can't take it for whatever reason, or if it changes into another material at that temperature, then this isn't going to work. And when we're talking about making conductive ITO coatings, this is definitely the case, where if you heat ITO up in a vacuum, as far as I know, it reduces itself back down to base metals, and it doesn't work. So an alternative process is called sputtering. And this works by accelerating gas molecules and slamming the gas molecules at very high speed into the surface of the material with which we want to make the coating. And when that happens at just the right energy levels, it actually chips off a few molecules of the surface, off the surface of this material, and they go spraying off into the chamber, and eventually they'll land on the thing that you want to coat. So here's a cross-section view of the sputter gun. The ITO disc is the thing with which we want to make the coating, and then we've got our magnetic pole piece here with north and south poles. It doesn't matter which is which, I don't think. The idea with the pole piece being that the magnetic flux goes through the steel and then back up, through here. So the magnetic field lines look like this. This whole intersection here is at about negative 1,000 volts, and the outer section is at 0. So when we pump down the chamber to a very low pressure and put our 1,000 volt potential difference on here, the remaining gas molecules in the chamber will ionize, basically just like they do in a neon sign. And the trick with the magnet is that it concentrates all of the electrons in this area. And it does this because the electrons are relatively lightweight and they have charge. So the moving electrons are affected by these magnetic field lines. In fact, they actually spiral around the magnetic field lines. So we've concentrated all the electrons in this area. However, it's not the electrons that are actually doing the sputtering for us. What happens is these spiraling, fast-moving electrons end up ionizing more gas molecules. And it's actually the gas molecules that are attracted to this negative potential and hit the surface and cause the sputtering to happen, which is why this is negative and the shield is relatively positive, or at 0. This negative voltage attracts those positive gas molecule ions, and that's what causes the sputtering. The reason that we use argon is because we don't want an incoming gas molecule to react chemically with our material here. So for example, let's just say we were sputtering aluminum and we had oxygen up here. What might happen is a really energetic oxygen molecule might hit this and create aluminum oxide. It might not actually sputter the material, it might react with it. And sometimes that's desirable depending what kind of process we're doing, but generally you'd want to control those gases very carefully. So for a lot of sputtering, we just use pure argon. The exact pressure at which this whole process works is very critical to determining the success of your coating. So if you have no gas molecules up here, obviously the process doesn't work at all because there's nothing to cause the sputtering. That's at a really, really high vacuum. At really, really poor vacuums, if you have tons and tons of gas molecules up here, it's true you'll certainly be able to slam them into the surface. However, the high pressure is such a good conductor because there's so many ions, it's tough to get the voltage high enough so that the incoming ions are going too slow to cause the sputtering to happen. You'll have a nice glow discharge and things will look like they're working, but you just can't get the voltage high enough without, blowing everything up basically. Another problem is that if you have tons of gas molecules up here, when you eventually do sputter off a piece of the material, it's going to interact or it's going to hit those gas molecules. And that may or may not be a good thing depending how your setup is configured. So if your surface to coat is kind of up here, you generally want these sputtered molecules to have a fairly clear path toward it. If there's so many gas molecules up here that a lot of the sputtered material interacts with the gas and kind of starts flowing, that may be a bad thing because they're going to escape and coat other things on the surface of your chamber. It seems in the literature that most people prefer 10 to 100 millitorr for proper sputtering pressures. But it's also very common to use the diffusion pump anyway and pump the chamber way down as low as you can get it basically just to clean everything, to get the water molecules and everything to evaporate off the surface, and then backfill it with argon back up to the pressure that you want. In my first few experiments here, I've noticed that controlling the pressure is actually surprisingly difficult and also, as the literature says, has a pretty profound effect on how the sputter process is going. I've been using an electrophoresis power supply for my first attempts here, and it turns out to be a very non-ideal power supply for this purpose. Besides all the stupid safety interlocks that make it difficult to use, the supply goes into its current limit condition kind of too quickly, and it's hard to get a consistent voltage current out of it. It is nice that it has a constant power function, so you can actually set a desired wattage and then play with the chamber pressure, and it will balance the voltage and current without exceeding that power limit. However, I think for future experiments, what I'm going to use is just a microwave oven transformer with the standard diode and control it with a variac.
Now, let us come to our second last slide for today's module, and if you see the slide, the sputtering has advantages and limitations. So, what are the advantages? If you can focus on the slide, we will see that the advantages of sputtering system are large size targets, simplifying the deposition of films, uniform thickness. Second is film thickness is easily controlled by fixing the operating parameters and simply adjusting the deposition time. Then the third advantage is control of the alloy composition. Along with good step coverage, grain structure is easily obtained through evaporation. Sputtering cleaning of the substrate in vacuum prior to film deposition. This is very important because every time if you want to clean the system before deposition, it is very easy to use sputter compared to the e-beam and thermal evaporation. Finally, device damage from X-ray generated by e-beam is avoided. In case of e-beam, the secondary byproducts are X-rays which will cause damage when you create MOSFETs in particular and other transistors, and that is why the device damage if you use sputtering would be minimal. While when you talk about the disadvantage or limitation of the sputtering system, there are several such as high capital expenses, rates of deposition of some materials such as SiO2 are relatively low, some materials such as organic solids are easily degraded, finally greater probability to introduce impurities in substrate because former operates under a high pressure. So, these are some of the limitations. While we compare the e-beam and sputtering, then we can see that if you compare the rate, choice of material, purity, substrate heating and several other parameters, then you will find that the sputtering is way better in lot of applications, lot of parameters compared to evaporation. However, depending on the application a person will select or a scientist should select or a researcher should select a type of technology, if I just want to create a contact layer of aluminum, I will rather go for evaporation than for sputtering. But if I want to go atom by atom layer then or one atomic layer per second, then we can go for sputtering, because in thermal evaporation is not possible. Also if I want to see any source, then I can use for sputtering compared to thermal evaporation, where the source melting point is very important. When you talk about purity, the purity of the evaporation is little bit better than sputtering, while the substrate heating in the evaporation is less, and in the sputtering if you use magnetron, the substrate heating would be less, but if you do not use magnetron, the substrate heating would be substantial. Then we talk about surface damage, then adding bombardment damage in sputtering is possible, while in the case of evaporation you have a very low, but there is a generation of X-ray. In situ cleaning, which is possible in sputtering, it is not possible in evaporation. Alloy composition to stoichiometry, we have little or no control in case of evaporation, while in case of the sputtering it is tightly controlled. X-ray damage, like I said, only in evaporation, where radiation with particle damage is kind of possible. In sputtering, decomposition of material is high in evaporation compared to sputtering. Changes in source material, this is very easy in case of evaporation, while in sputtering you have to, it is little bit difficult, as you can see, as you have seen from the video. Scaling of the system is good in case of sputtering, but while in case of evaporation it is difficult. Uniformity also is better in case of sputtering. When we talk about large area, capital equipment is also more expensive, sputtering is more expensive than evaporation. Number of deposition, many deposition you can do can be carried out per target, while only one deposition per change or per charge. Thickness control is possible in sputtering, with several controls possible, while in case of evaporation it is not easy. Finally, we have adhesion. Adhesion in sputtering is excellent, and that is why when it is about the metal adhesion, people prefer sputtering over the evaporation. However, the shadowing effect is also less or small in case of sputtering and compared to evaporation, that is why you have better uniformity of the film, also step coverage. Finally, the film properties such as grain size and other parameters is difficult to control in case of evaporation, while in the case of sputtering is very easily controlled. So, if I want to have a summary is physical vapor deposition consists of three techniques. One is called thermal evaporation, second is called sputtering, and third one is called E-beam evaporation. Right, thermal evaporation, E-beam evaporation, sputtering. So, is a technique based on the formation of vapor on the material to be deposited as a thin film. The material in solid form is either heated until evaporated, right, or sputtered by ions, while in the last case ions are generated by plasma, which is the sputtering case, right, within an inert gas. It is also possible to bombard the sample with an ion beam from external ion source, and this will allow to vary the energy and intensity of the ion reaching to the substrate. So, this is the last slide for today's module, and I hope that you understood the process of how this sputter system works and how the E-beam evaporator works. In the next classes we will be looking at the lithography system, some of the videos on lithography, and then we actually start fabricating or process flow for fabricating several sensors and transducers or sensors and actuators. So, till then you take care, look at the this particular module, understand the technology, right. The idea of you of me showing these things to you is to make you familiar with the technologies available for depositing several films, whether it is metal or semiconductor or insulator. Alright. So, till then you take care, I will see you in the next class.